Hey, how's it going?
It's going good. How's good? Did you
So
read my article? I saw you liked it.
yeah, I did. What do you actually use for it? Like, do you use some kind of a graph representation to do it?
For
You're
what?
predicting properties of molecules, right?
Yeah.
So how do you what did you actually do to represent?
I mean, when I was helping the professor, I wasn't representing the molecule, but I was predicting certain properties of the molecules.
Right.
Those were structural inputs of the molecules, like entropy or some other things that I forgot. Something I forget, like different.
Okay, so they were already
like some energy
properties.
level or something like that. Those properties, sorry, and they wanted to predict some other property that is correlated with these properties of a new type of material, and it typically takes them several months or like at least a month to even if they want to actually create that material and then predict the properties. So with machine learning, they can do it like an hour, and so it's a huge leap. It helps them really fast track their research. But now the thing is, whatever they predicted, they need to verify it, whether it's holding true, and so they can cross-validate it with their data, but then now need to see whether it actually proves right.
Yeah, it's verifying reality all the time.
Yes. Yeah, but very promising results, really. Yeah, with very, very small data set. The data set I worked with only had 14 molecules, so it's hard to create even one data point. So I told the professor, I was like, this is ridiculous. You're giving me 14 data points, really? And he was like, do you know how much work it takes to get even one?
Because maybe one interesting possibility is so you're using kernel methods anyway, right?
I just did very basic stuff for the professor. Like I just did lasso and bridge, and I didn't implement kernel regression. He just wanted me to give him some exposure and then do like a lit review. So I told him that because I didn't have as much time to implement everything, but I said this is the direction if your PhD students want to do this.
Because if you were doing a kernel method already, you could just do a kernel for the properties you have, but there are also things called convolutional kernels, which are like if you have data that isn't like normally you want to do machine learning on data that kind of fits in a table, right?
It is rectangular data.
Right, but in some sense, if you're dealing with things which are like sequences or graphs or things like that aren't actually tabular, then convolutional kernels are kernels where essentially, well, because kernel methods work just from a similarity matrix between atoms anyway, right? So it's a way of sort of giving two graphs a similarity by essentially how many subgraphs, what kinds of subgraph arms with some systems exist. And people do, now once you get that similarity matrix, then you can do a kernel regression based on the convolutional kernel. So you could try to actually predict stuff directly from the actual structure.
Yeah, I didn't read any of that. Whatever they've used the material science so far. But that's an interesting side.
So basically it's like this normal sort of graph machines, there is a really good way to like represent like if you track a property like something that just aren't fit in paper. It's not a set of numbers. It's a graph.
Right now I'm in
bunch of graphs. It's normally a lot of this way. So pretty much every other method wants you everything to just be a row of numbers.
Yeah, and then one more.
Whereas with kernel methods, really all you need is a similarity between items. You can actually work together similarity on graphs.
That is what I'm big in optical transport as well. I don't know if someone
Okay, nice to meet you.
transporting or using the similarity of grids as the grid, right?
Oh, developing.
Because there could be like 10 points in domain A that you're trying to transport to another point How's everything going at your
I want to use also machine learning.
It has been a
roller coaster, too much work,
Yeah.
you've been swamped.
yes, all of the above. All of the above. So, since, well, let's see, I guess you haven't been to a whole bunch of meetups, so.
Yeah.
Because my internship was ending, so I was swamped. But, yeah.
So, I think all of the above happened.
Yeah.
Video went bankrupt. Then,
Oh my god.
the week we were gonna go bankrupt,
Working,
we
yeah.
signed up a client who happens to be JPM. So we went from
Log,
being bankrupt
logs
to being,
Massive.
I'm like,
hey, log
I'm trying to find a similarity
Good way.
in different events.
They were restructuring it. And they cut one of the teams, and it's actually they cut the team that got rid of.
There's
Yeah.
Yeah, a little bit of that.
So they cut that team.
Just trying to find,
So
what
sort of been putting
one,
it in touch
like trying to see if I can
that I know.
group,
Yeah,
if we can group
what
different events together into like one incident.
So his original background was he was a philosopher. I think linguistics too, but so he's worked more in the sort of knowledge representation of ontology, something like more that fine, that knowledge graphs, concept graphs. That's more his area more than machine learning. But I'm kind of happy for him.
Yeah.
I mean, you know,
Yeah.
he's
I
not
don't
going
imagine
to
that
be.
he would have a hard time finding
No.
something.
So that's gonna.
That's why I was wondering, I was like, where's how come you're a low group tonight with your friend?
Well, no, I mean, he hasn't been going to watch you anyway. Before I think he's.
We have pizza here, so before we get started, I'm gonna come and grab some drinks.
This is called something, right? Like the second half of August. It's called something in Italy. It's some type of European holiday. Some religious holiday.
No place to
It's
begin.
like,
It seems to be just general.
hey, sorry.
We might have to do that.
Hey, how's it going?
Yeah. Did you eventually figure out the lunch plan with now?
Working on implementing the needs.
Yeah, I
Like
finished that.
in browser in JavaScript. And it's very good. So today I started testing it.
Yeah, were you there?
Roles this with pressure.
Yeah, it's good.
Carlos. It's like environment in JavaScript where they go to
We don't have any plates.
So it's the one thing
I know. And like when you're
they just they trained it back in for the front end, like the JavaScript stuff. They just ran the just images, so images. But that one is like actual environment, like
Did you get it?
no, I'll make your mind.
Oh, okay.
So I also think so. You're gonna try to.
Yeah, I mean, I've been hearing.
You're assuming there wasn't.
And I did that to afraid that LinkedIn will go on with every personal notification that I was just like, I basically wanted to say, okay, I've ended my internship, now I'm back to school, and LinkedIn just back. So eventually I deleted that job. So I was like, people need to stop wishing me congratulations. This is just 50 years, oh my god.
But I thought it might have been sometimes agents are sort of like, in Australia, sometimes they were like, like on the way of like just getting elected.
Or like that.
Yeah, like
When you leave, all the students are either funded by, I mean, you have to be funded, so either you're an I did an assistant lecture. It's not that staff, we something that people do.
Okay.
I eventually responded to all the calls. Sorry, it's not my I'll put it after a couple of months. Because also I felt like I just posted the article. I don't want the attention to go away from it.
Yeah. No, this is a little more clear over there.
I mean, is that what you
Oh no.
Development skills, maybe they're the same, but not, just kind of like something,
They started doing that. Usually the first article they show you when I finish is usually still enjoying it. Yeah, it would be, but it's like for the more specific issues, just random, you know, how to be an aspect of machine learning.
Good job.
everybody have to say that. They've never done it.
I'm not a person that makes restaurants or something. Yeah, I like the food, but it's not really like, I want to see how they work.
Okay, cool, yeah, no worries. I don't want you to feel
Yeah. No, for me, it's that's a few that I really like, and you know, if I hear one that's kind of different, I go there, but I'm not a like I don't do restaurants as everything.
How's it going on? Usually I thought you were Indian because of Thai, like
Oh yeah.
but you didn't have any Indian manners. So I was like, how is this? Like, there is like this person even if they're born in India. So I was like, something's wrong about this guy. His name is Indian. I said there's like an Indian name Abhay, which is A-B-H-A-Y. So I thought this guy is Indian, but he speaks his name. I was like, he doesn't like behave Indian and what? Yeah, then he told me he's from Kazakhstan.
By Indian manners, I mean something like in that.
I think just in the body language, talking, humor, style of humor.
That's why control is different from like from the whole because like control more types of things.
Are you talking about like being Indian and not okay?
How do you react?
Yeah. I remember when I was new to the US, I told my advisor as a joke in this course, don't give us this homework, and he took me seriously. And I was like, okay, that's it. American humor and Indian humor are totally different. Like, he was supposed to not listen to me and still give the homework. Yeah, he just didn't get it. He took me seriously. I was like, whoa, that joke is not bad.
Yeah, I found when I first came to America that like, wow. If you're going to be sarcastic, you've got to be really obvious about it.
Yeah.
You've got to go like,
Hasn't been here so long.
Yeah, but in India, everyone would get it, you know? Like, in India, would just respond, oh, really? Of course, I'm going to give you that homework, but you know?
Yeah. His company blew up.
Stem silence.
Push child for startups. year,
Yeah.
within a year of its inception, it was valued at
No, now I
it's
do not
27
not
million.
forecast tracking fuels, like,
valued at 125 million.
unless they get to know me, like once people get to know me, or I'll crack really obvious.
No, but they figure out how to make money. So that was also after 1 year, they did around.
Yeah, I'm pretty picky with the just like,
So they are,
because like
within
the
a year
just
they
started
had
out around 10, I was
200
attending all the like.
and within 2 years they have, I'm not gonna get the number, 400.
What about you? Are you going to like do $10 now? I
So
see my
here's
call,
the data science thing.
The smallest company with the
I got about 4 minutes in the section there.
Black
Oh,
was like,
yeah.
was he black or was he like?
They're a company. They're a startup.
I heard black logo. Black logo, okay, I don't know this meetup.
Yeah, did you go to Black Well, this is for machine learning.
Sorry, what?
Did you go to Blackwell?
Yeah, the meetups at Black Locust, I used to go to.
I
I used to work, well, co-organized. I used to work at Optical
Oh, okay.
a lifetime ago.
I wasn't there when black logo.
Megan was the
Yeah, Megan, yeah, I remember Megan.
I helped her as the
I haven't seen one of those up in forever.
just as I left Blackwell, because that was like 4 years ago, something. They had made a decision that they were going to host meetups. Those got to the point where they were hosting all of them. Awesome. A lot of big ones. What took?
So they just went for 30 like you
They made a decision that they were going to do it. A couple of machine learning meetup died as a result.
Yeah. Good. And that was actually pretty much the deal. One I actually kind of like. Like most of the other, and even that one was kind of fairly bad, but a lot of them are sort of beginner, you know, how to be a data scientist in 6 months kind of.
Oh, nice. It's not your cup of tea.
Just not entirely. I want to take my time, you know, it's my right. Actually the Scout meetup. I used to do a Scout. Nowadays I do it.
I talked for like
Then I like the
Go to those, right?
But it can come through graphite.
That might be.
And usually like the monthly like do the short and other so they don't just
Hey, let's go ahead and get started, please. Thank you, everybody, for joining. My name is John Ramey. I'm one of the organizers for the meetup. Our pizza tonight was brought to you by the large accounting firm KPMG. We have some connections there, so they've been paying for our pizza. Special thanks to them, and also Capital Factory for hosting. A couple things to note. So I lead the data science team at Novi Labs. It's a startup. It's booming. We are in the oil business, so if that turns you off, not going to apologize. Our company is doing quite well, and we are hiring full stack and data scientists. So please see me after if you'd like to talk. Also, I'm supposed to plug OpCity, which is another company run by one of our co-organizers. I'm not going to plug it as much as Novi. I think they're hiring or something. We have a couple talks lined up. I've been working with the speakers, trying to get things pegged down for September, but I have not.
I've got a couple for you, by the way.
Awesome. That sounds great. If you do have any talks in mind, please see me after. We're ping me via Slack. Speaking of Slack, I haven't plugged it in a while. Summer, people have been traveling and all that. Please join the Slack channel if you haven't already. Until summer hit, it was fairly active, a lot of conversation, especially in the more advanced meetup room. A lot of discussion, a lot of good discussion. So if you want to sign up for the Slack channel, the easiest way to do it is go to the meetup site, scroll down to the bottom of the page, and there's a link. We've plastered that link everywhere on that site. So there's a bot that we made a way back, and you just click it, put your email address in, and it'll invite you to the Slack channel. That's all I had this evening. I'm going to turn it over to Vincent Marin. When I heard about his talk, I was pretty excited about it, because when we first started the meetup, we actually were trying to get people to talk about style transfer just to check that box. A lot has actually happened in style transfer since we started the meetup a couple of years ago. So we never actually did the beginner one. And it's like nowadays, that's just like standard blog post material. I'm really excited about this one. So let me turn it over to Vincent. Thank you so much.
Cool. Thank you. So yeah, today we're going to talk about style transfer. So I figured the best way to introduce it is to play a little video, animation. So basically we have the visual style here, and we're looking to transfer that visual style onto these other images. So we're showing like a static image on the left, and then frames on the right are steps in gradient descent as we converge the image on the right to reflect that initial style. So now we'll step through with a different style. And so, yeah, the basic idea is you come up with some notion of visual characteristics that represent a visual style, and then some way of defining a distance between various styles. And you descend the gradient of that distance or loss function in order to generate an image that looks like this. And we'll do one more, and I think you pretty much get the picture of what's going on. So yeah, John was asking for different people to give different talks. This is kind of a method I came up with about a year ago when I was looking through some of the style transfers. And my background is in statistics, and in particular in finance, like finance applications of statistics. And the math basically that was being done to conduct style transfer didn't totally add up to me. So I thought about reorganizing it in the context of style transfer. And hopefully today I can explain or provide some intuition of why that makes sense, and then it would be even better if I could give you some ideas of different kind of like mathematical approaches to analyzing these. But I'm going to start with the historical development of style transfer, which began with kind of like dot patterns and different kind of analysis of the human visual system. And then we're going to talk about a little bit about general optimal transport, and then construct style transfer as an optimal transport problem. And one of the cool things about that versus other approaches, you don't have any parameters. So a lot of the style transfer implementations you can find, they're like dependent on very specific parameters or ratio of parameters that kind of need to be set for different image combinations. I think when it's constructed as an optimal transport problem, it works pretty well without any parameters or calibrations, just out of the box as a general algorithm. And all of the code is here on this website. So as I mentioned, my background is in statistics and finance. I gotta assume that everybody here has kind of some knowledge about deep learning and CNN architectures and so forth. If I'm going too fast, just like raise your hand and maybe ask a question. And if things are going slow, like give me some body language that you seem really, really bored, and so I'll know to move on to something else. And again, yeah, this was just a fun little project I did about a year and a half ago. I thought it would be cool to make some slides as a presentation. I think it might have some applications to other fields. Personally, I work in finance almost full time. I've become more and more interested in kind of edge applications of machine learning of late. So working on some things related to that. But in general, this is just kind of a demonstration of a project that I thought was pretty cool. So historical development of style transfer. If we look back, this guy, Bela Jules, was one of the kind of really geniuses of the 20th century. He developed a lot of the stereograms and various dot patterns for diagnosing different visual ailments. And he asked an important question, which is a little bit of a mouthful, but it is, what features and statistics are characteristics of a texture pattern such that texture patterns that share the same features and statistics cannot be told apart by pre-attentive human visual perception? So this was basically wondering what types of patterns, which patterns that are specifically different but share certain characteristics are indistinguishable for peripheral vision. Then fast forward to about the year 2000, there was a lot of work done on the notion of texture synthesis. So if you stare into the center of this image, you're going to see some yellow peppers that look pretty healthy, and they look totally normal, and your brain might complete the picture and see the whole image, like the whole periphery of the image, as those same yellow peppers. But if you look outside the box, you realize the ones outside are totally inedible and they're like computer generated. So what Portilla and Simoncelli did back then was they hand-engineered features. So they were kind of like spatial autocorrelation features, covariances, and different Fourier coefficients that when you matched those specific features of a given pattern, you were able to kind of replicate the pattern by modifying initially just static noise to exhibit a specific texture. So, but the process was iterative in that they would work with a set of textures. So for example, like pictures of gravel or pictures of a carpet like this, and find the statistics that would allow that texture to be synthesized. And then they would try more textures until it broke it, and then they would add more statistics. So it was all totally hand done. I think it was a lot of grad student hours, but it's pretty cool. They were able to, I don't know. I think it was kind of an impressive image, but it was all done by hand. Like they weren't transferring knowledge or doing any type of like fine calculations in order to come up with this result. So then now, could we just get a show of hands? How many people here are familiar with convolutional neural nets or CNNs? So I'll make this pretty quick then, but broadly speaking, a CNN will take, the general architecture is to take an image. Here we have a picture of a car, and it'll apply kind of like convolution filters to overlapping sections of the image in order to process the raw pixel red, green, and blue data into more and more abstract features. So at very shallow layers of the network, that's going to be like edge finders. To what extent, for any portion of an image, it'll quantify to what extent is there a vertical edge here, or is there a gradient from red to blue? In middle layers, it's going to be kind of more abstract, like combinations of shapes, and then at later layers, it will be very general things like, to what extent is there two eyes, a nose, and a mouth here, and are the ears pointing upwards in order to determine the odds that it's a certain type of cat or dog. And that is kind of simplifying things, but in general, you go from very basic shape detection to more complex feature detection. And some cool projects were done where they looked at CNNs and they found they optimized for input images that would maximally activate specific neurons. So here we can see that these are for basically like rather early layers. You're just finding these very basic shapes that cause that neuron to be most activated or maximally excited. Then we get a little bit more complex shapes that kind of look like tires or maybe eyeballs, but they're certainly, you know, maximally activated by circular shapes. And then here we have, you know, things that look like noses and kind of honeycombs and stuff. So the shapes get more complex. In this next slide, you know, you can't really see it that well from back there, but it shows a similar thing, but each of these cells of 6 images are optimized to be maximally diverse from one another, yet still provide very high activation for the specific neuron. So the point here is like that it's not like a neuron is looking for one specific input stimulus, but there are many different stimuluses that could provide a very large activation. So for example, I'm not sure how well you can see this row, but there's like something that looks kind of like an eyeball in red and green and a more purple hue, and they're all providing very high activation. So these might be looking for some type of specific, or corresponding to some type of general notion of an eye, but willing to accept some variance in the different colors. But the general idea is a convolutional neural net could be thought of as, you know, taking an image and decomposing it into a much larger and larger feature space, and then running some calculations on that feature space to determine what is in the image. And so pretty much everything we're going to talk about today is only concerning the notion of decomposing the image into, you know, a quantification of the various visual features, and not concerned with the point of the CNN initially, which is to classify images. So all of this notion of style transfer is kind of interesting in that regard, because it's reflective of transfer learning. Like, we're not, although the network here, which is the VGG network, or Visual Geometry Group, which built this network, what they're trying to do is predict what's in the image, and you can use that same engine and all of the parameters they've trained to do that in order to do this thing called style transfer. Okay, so now the main paper that develops style transfer. How many of you have read this paper? It's the Gatti's paper from 2015. No. Okay, so the main idea with style transfer is you have, well, in their construction of style transfer, you start with a style image. So here it's Van Gogh's Starry Night, and you have a content image, which is a picture of like a riverside in Germany. And then you have a noise image. You define content loss to be the pixel-to-pixel difference in CNN activations at a rather deep layer of the VGG network. So like the specific differences in the activations squared, the sum thereof, is like how much are these two things differing in content. And then the interesting thing is the style loss, which is basically, rather than comparing the images on a pixel-to-pixel basis, you're taking aggregate statistics. So they use a non-central second moment, or a gram matrix, where basically what you're doing is you're taking the tensor of activations and you're unwrapping it, or you're flattening it basically. So you're disregarding where the pixels are in terms of height and width in the image, like X and Y coordinate, and you're only paying attention to the CNN feature activations. You're taking an outer product of that, and you're comparing the outer product of the style you want to replicate with the noise image. So then you end up with a loss function that is a combination of your style loss and your content loss. And by minimizing that, you're able to move from a noise image to an image that represents the content in the specified style. So these are a whole bunch of examples, and I think, you know, they all look really good, and the paper definitely achieves what it says it does. It's able to take an image and reproduce that image or something that looks like that image in a whole bunch of different styles. Now, one of the things that's kind of a bummer about this is there's some hidden parameters, or not hidden, but there's just parameters that are very calibrated. So you'll see, like, in order to generate these images, the ratio of A to B was 1 times 10 to the negative third for image B, 8 times 10 to the negative fourth, 5 times 10 to the negative third. So there was a little bit of a hand calibration, which is a little bit frustrating if you want to replicate something for some other images to know that you need to come in and toy with these things. Then when I was reading this, I thought it was really odd that they were comparing non-central second moments. A lot of statistics is based around covariance matrices or central second moments, and different. There's been a lot of work done to establish like distances between probability distributions, which we'll get into when we talk about optimal transport. So to me, I thought maybe there's an opportunity to adjust this math a little bit and restructure the problem.
Could you quickly say what they were the second central moments of?
Non-central second moments?
Right. What were they actually like? So basically, you're just taking the sum of squares, right? Or
Okay,
the
so
average of squares. But what is it you're taking the average of squares of? Just the image, or?
okay, so you're taking the image and you're flattening it. So let's say your image is 100 by 100 pixels by 100 pixels by 64, convolution filter feature activations.
Okay.
So you're taking that as a 10,000, the 100 by 100 by 64 matrix, and you're taking an outer product with itself so that you get a 64 by 64 matrix, called a grand matrix, but it's a non-central second moment because you're just multiplying everything with each other. So like a big map mall.
You're basically multiplying a thing with its transpose, essentially.
Exactly, yeah. And so that, here they call that A to the L, which by that they're referring to a specific layer on here, and then G to the L is the same thing for the image they're synthesizing. And so this is it's a matrix norm. They're taking element by element differences, square differences for the matrix. So they're weighting like the off diagonal terms just as much as they're weighting the on diagonal terms, which also is a little bizarre, from a statistical standpoint when you're used to dealing with central ones. So yeah, but the general idea, of style loss is to take some aggregate statistics of the activations over the image generally, and take a norm from one to the other. So yeah, that is Vigatti's paper. So now a little bit about optimal transport. So I was thinking about how to explain this, and I think a good way to think about optimal transport is to think of something like, if you want to get from the Texas Capitol to Austin Airport, there's a distance, your Euclidean your distance as the crow flies is something like 7 miles, but that's not a very practical distance number for anybody to know when we're used to traveling on roads. So you can go into Google and it will evaluate millions of potential routes, which frankly, you could have a suboptimal route. Like there's definitely ways in order to get from the Texas Capitol Austin Airport, you could drive up to Dallas, turn around and drive back. All you really care about is the optimal routes. So implicit in finding optimal routes is a full transport plan. So then kind of your gradient is the gradient or derivative of your distance is your transport plan. So if you're currently standing at the Capitol and you want to get closer to the airport, the specific instructions you get, take it right here, get on I-35, would be the optimal transport plan. And that, that's the same thing as a gradient or a derivative of a loss function. All right, and then one other idea, this is a little bit more out there, but one other idea about optimal transport that hopefully this gives you the intuition is, pretend you're on a golf course, but instead of having numbered holes, you press a button and 9 balls randomly drop out of the sky and 9 holes appear in the ground. So how do you go about choosing which ball to hit into which hole if your goal is to hit each ball into a hole in the minimum number of strokes? There's a lot of different options because you have, it's 9 factorial in order to assign 9 balls to each holes. So this problem would be a lot harder than just playing normal golf because first you have to do some huge programming problem. Yeah.
When you say minimum number of strokes, do you mean to minimize the distance between the ball and the hole you're hitting it into? Total, the sum of distances?
Well, that's one thing. I mean, you could say, I'm just saying, using a golf example, like, if there's a sand trap, to overcomplicate things.
Oh, I see, because the distance is not just a crow fly's distance, it could be varied by the path, it's path dependent.
Exactly, yeah.
Yeah.
So,
And one ball each hole, so even if they're all
Yeah.
clustered around one hole, you still gotta.
Yeah.
so optimal transport sometimes deals with discrete problems where you have, for example, like you have coal mines that are producing coal, and you have power plants that can use coal. And you have some distance cost for transporting the coal between the two. How do you optimally do it? When sometimes you have very large capacity at certain power points and very small capacity at certain mines. But in general, the physicist approach to optimal transport usually is when this number 9 tends up towards infinity, so we're dealing with continuous distributions. And that's kind of the approach we're going to utilize to do style transfer when we're describing a continuous distribution. So one Wasserstein distance, we'll stick with the analogy of golf and say that we have a random variable x, which is the position of the ball, and then we have a random variable y, which is the position of a hole. And then we have distance, which could be the Euclidean distance, or it could be just some estimate of the number of strokes it would take you. Are people familiar with the concept of infimum?
What?
Infimum.
Oh, infimum. Yeah.
So basically, Wasserstein distance is has a notion of optimality baked into it, because basically what it's saying is you're taking the infimum over all of the possible couplings. So if we have our balls x distributed according to some distribution phi, and our holes y distributed according to theta, we have a whole bunch of different ways that we can couple them. You could think of it as joint distributions, or sometimes people prefer to think of like orthogonal dimensionalities. But basically what this is saying is the one Wasserstein distance between a set of distribution of balls and holes would be the optimally minimal, or the infimum over all possible couplings of the expected distance between the balls and the holes.
So basically, little g is a distribution over x and y.
It's a joint distribution, yeah.
As such that its marginal over x is phi and over y is theta.
Yeah. So one Wasserstein distance is has some interesting properties, but we're going to introduce the notion of a Gaussian in order to develop two Wasserstein distance, which is what we'll use to do style transfer. So
when you say coupling, do you mean it's not a one-on-one mapping between x and y, right? Multiple x's can contribute to a single point in theta, in the distribution theta. Or is that
well, in discrete senses, if it were we could replace infimum with just minimum if it were a discrete number, for example, 9 holes and 9 balls, and then it would just be an assignment problem. But if we have infinite, you could think of it as a coupling or as a joint distribution of, whatever, let's say x is, we'll say x is 2 dimensions, so it's like some physical location on a golf course, and y is also in 2 dimensions. Then your joint distribution space would be in 4 dimensions.
Find theta is the same, then the infimum is always the diagonal, right?
Yes.
Which is kind of what you want.
So if we introduce Gaussians, they're just really clean distributions. Probably you're all familiar with it as like a normal distribution or under the notion of a bell curve. But the main point is that you have some symmetry along eigenvectors about your mean, and the distribution is fully characterized by the first 2 moments, so it's the mean vector in a covariance matrix. geometrically, you can think of it as having equidensity contours that are ellipses. So as you move further and further from the mean, like your density will decrease with your rough radius. You know, as you have larger and larger ellipses, your density at the perimeter thereof would decrease. So now the cool thing about Gaussians is your L2 Wasserstein distance can be expressed in closed form. So if you take an L2 norm as your definition of your distance between x and y, the L2 Wasserstein distance between two Gaussians has a very crisp calculation that you can run. And the gradient of this becomes an optical transport plan. So if you had, your golf balls were distributed normally, and your holes were also distributed normally, the transportation assignment problem would be much easier than if they had, you know, a non-parametric problem, a non-parametric distribution, or, you know, some other general distribution, because of the specific characteristics of the symmetry. So if we want to develop style transfer as optimal transport, basically the way to think about it is you pass a style image and a subject image through that same VGG CNN and extract your activations from the convolution layers, and you calculate sample mean and covariance matrix of the respective feature vectors. So like if we passed in this initial image of a car, at this point our 228 by 228 by 512 feature block that's describing the image would be thought of as 784 samples of a 512 dimension random vector. So we would take the mean, which would be a 512 dimension vector, and the covariance matrix of the activations across the image, which would be a 512 by 512 matrix. And we would apply that L2 Wasserstein distance to those matrices in order to calculate the distance. And then the gradient of that sum with respect to the subject image is the transport plan, that when you take steps in that direction, you synthesize the image to start to look like the other image. And yeah.
What does it mean with respect to the subject image? That's where I'm not quite understanding.
So you have a style image that you keep static. So in those examples, it was like pictures of the mosaic or like the various paintings. And then you have this subject image that you want to modify in order to have it represent the style. So you take the gradient, like if the subject image is passed in, you calculate all of these means and covariances, and then you take the gradient of your distance function, which is the sum across all of the layers, and you back propagate that to your initial image as a variable. So your the gradient with respect to the initial pixel data of the subject image. And it doesn't require any parameters because you're just taking the sums of these distances. So you don't have to have any notion of content loss or anything. Yeah.
So if you used a different distribution other than Gaussian, would you basically be non-symmetrically applying the style transfer to the new image, aside from difficulties that you may encounter from like a not easy to use distribution?
Yeah, I mean, you could have another, the reason I immediately was, it was intuitive to me to use a Gaussian distribution is because they're just very computationally tractable. You could potentially do something, I mean, it would need to be a distribution that spans positive and negative numbers, so you could find something else. I think the advantage of the Gaussian is it is computationally tractable, and basically because it's totally specified by its mean and its covariance matrix. Does that answer your question? Yeah.
So to put it another way, you're taking your style image and your subject image, and you're calculating these summary statistics, and you're moving the subject image towards the style image until those converge. So you're using the gradient descent to just move. Really, if you just knew the answer, you could do the modification, but you're doing it through gradient descent, where you're modifying the image such that the summary statistics eventually converge together.
Exactly, yeah. And I think it'd be a good idea. Sorry?
You get to really low loss, right?
Yeah, definitely. So like, we'll just go back and watch another one or two of these. But so starting with this, you know, we pass this image through the CNN and calculate the mean and covariance of the various convolution filter activations across the image. Then we would feed in the image that's going to be right here. And initially, what that math kind of decomposes as is it's like, which portion of this image can I transform to look a little bit more like a portion of this image? So it's saying, you know, where am I close such that my modifying a pixel, changing a red to a green and so forth, would allow my overall style, you know, to be represented in the new image I'm synthesizing.
So could you repeat at what level you're comparing the features?
Every level.
At every level of the network, you're
Yeah.
doing this distance.
Yeah, so you're just
And then
taking some-
why, can you give any intuition as to why doing that corresponds to the human word style? Right, you're just comparing these, so you're making these numbers closer to those numbers, but why is that
Yeah.
style?
Yeah, so what I would say is like, if a CNN takes in an image and quantifies visual characteristics, like style could be viewed as a probability distribution over visual characteristics. You know, like it's, to what extent are vertical edges present when red goes to blue, you know, for the very shallow layers, and then for the more deep layers, like this, I think this will be a good example. We've got this kind of, you know, curly style. Like, those are probably more represented in the deeper layers, but this algorithm will just take the distance at all of them and cause it all to converge.
And are all the layers weighted equally?
Yeah, you just sum them all. So if you're very distant at certain layers, you know, you'd look to minimize that first, and then if you're very separate at other layers, you would, you know, if some distances become close to zero, the other, you know, the gradient will look to minimize the other distances.
Right.
Just curious, do you think that there would be any interesting use cases to not do all the layers and to pick specific layers or limit them or you know, or weight them in a certain way?
Yeah, 100%. I just like, that's kind of the thing I was trying to get around, because I noticed with the Gatti's formulation, it's like, well, it works really well if you come in and choose specific layers and weight them in a certain way. I'm always a fan of like non-parametric methods where it's just you throw it all in there, and you know, if that causes it to converge, and it generalizes well to a whole bunch of different images.
But you might be able to do that. I mean, I don't know. I mean, you might have sort of you know, like you might focus on high level aspects and sort of deep into the neural network levels of change and only do those, right?
Yeah.
And
or if you wanted to do it really fast, just doing shallow layers would make sense because like you have a lot less computation. So definitely something you could play around with, but.
So just a minor clarification. So you calculate you have this network which is fixed, and then you calculate the feature vector for the style image, and that remains fixed, and then you constantly try to move the feature vector of the subject image towards the style.
Yeah, correct. So that's a good point. With like a normal CNN, if you're training it, all of your weights and biases and so forth, those are all variables, and you're looking to train those. Here we take all of the weights of the network and assume that, you know, we're fixing them as completely static. And then we're also fixing the style image as completely static, and we're just modifying this other image in order to bring it closer and closer to exhibit that style. And we're totally getting rid of that notion of content loss, which, like, the kind of philosophical reason would be that if the transport instructions are optimal, you're just going to change the image as minimally as possible in order to represent the style.
What's the loss function for the transforms you're applying to the original image? Like from so you're trying to get the values in the nodes from the style image to be as close as possible. But
yeah.
What's your cost from the
like L2 norm?
Just getting the distance to be zero.
So you don't have like a decoder. How are Okay, I understand that you move the picture and you through the network and then you get the features, right? And you keep back propagating. When you back propagate, I mean, eventually how do you get back the style transform subject image? Because you don't.
At every step you're getting it. Like,
yeah, but in the network every layer is becoming smaller. I don't know, did I miss something? Every layer is becoming smaller.
You're passing it through
Yeah.
in order to calculate these statistics. You're calculating the statistics, and then you're differentiating it back with you're back propagating it with the image you're synthesizing as a variable.
Okay, so when you get it back, it's a bit transformed.
It's a bit different, and it's a bit different. So each of these frames, I think this is like 15 frames a second, and each frame is a step of gradient descent. So like, 3 seconds would be something like 45 steps.
Okay, so when it goes through the network again in the next round, it's the new transformed image that goes back.
Oh, yeah, yeah. Oh, okay, so I'm always starting from the image on the left, or I'm using 2 images here. And we're always starting from those images every time we change the style.
I think one way to think about it is, so because you're using the activation of the whole convolutional network, you're capturing both local and global properties of the image. And since you're doing gradient descent, you're essentially going in a direction which is favoring local transformations. And so you're going towards the style image, but making the local transformations first. And so that way you're keeping the semantics constant and changing the style, at least initially. If you kept going long enough, eventually you'd actually start changing the content.
I'm with you, but like, you end up converging to a point where it,
oh, so you don't stop early, you actually converge.
I stop early. Well, okay, basically you stop when BFGS tells you to stop, which is when your gradient is below machine precision. So basically it goes until you derive. I actually set it to do 100 steps or convergence, and many times it will converge before you hit 100 steps.
I am missing something, because I don't understand why you don't just converge eventually to the style image.
Because there are many, many images that will have the same summary statistics.
Yeah.
So it just wants to find the closest one.
And you're totally flattening with
I see. You're doing non-convex. You're doing a non-convex optimization. You're going to a local minimum that's near to where you started.
And you're also throwing away some of the position information and that flattening.
But I think that's the key. That you're flattening. So you're taking kind of like a summary statistic over the course of the whole image. So you're viewing this 28 by 28 by 512 tensor as 512 samples of a random vector, and you're just taking the sample statistics of that random vector, and then you're utilizing the distance between random vectors. So, yeah.
What was BFGS?
Oh, it's Braden. It's an optimization.
It's kind of like things like data grad and all of those things. It's a second order method.
It's a Newton method. It's a Newton optimization method that's non-stochastic for like when you have a really big problem. It's a good good method. Quasi-Newton method. Okay, so yeah, I thought this was pretty cool because you have no specific parameters, like all of these images and so forth. It's just you throw the thing in, and it seems to do a pretty good job for diverse number of like styles and content or images you're looking to synthesize. There's no notion of content loss, so your loss function is a little bit more simple than the Gatti's function, and it seems to work well whenever your style image has a repeated motif. Like, so for example, if you took a natural image, like a picture of me and a picture of, some trees and some hills, it'll do it, but it kind of just looks like gobbledygook. It really works well when you have, a repeated thing, like either a mosaic or brush strokes or like a paisley. And so I think it's a cool method. I think it would generalize really well to other instances where you have an inference model. I've been dying for somebody to come out with a really good like musical inference model, maybe like genre prediction, because I think that this could work well in one of those frameworks. I also think, it's tough to come up with examples that aren't silly, but like let's say you had some inference model amongst like food recipes, and you knew like you knew one recipe really well, but you wanted to change it to have some different taste profile. Like I think the potential for applications of this could be pretty broad, but I haven't done it on anything else yet. So.
Have you tried this with, oh, sorry.
Oh, just I was going to reiterate that all the code is available here if you want to check it out and step through exactly what happens. The L2 Wasserstein distance calculation it seems a little bit more complicated because in order to take square roots of matrices, you need to like do an eigen decomposition, but it all works out pretty well. It's written in TensorFlow. Feel free to reach out if you have any questions on it.
How fast does it run for a normal size image?
Probably, for running a normal size image with every layer, it's about 100 seconds on a GTX 1080 Ti.
Have you tried this with a randomly initialized neural network instead of a trained VGG model? Like there was an interesting paper a while back called Deep Image Prior, where they kind of found that there's a lot of inductive bias in the architecture alone. And I'm just curious if you had ever experimented with a non-pre-trained network.
So like VGG architecture random weights?
But with randomly initialized weights.
Interesting.
How much the architecture contributes to that process versus the trained weights.
Can you post that paper on Slack?
Sure. Yeah.
That'd be very interesting. I think a lot of people would want to look
Maybe we
at
can do it in the reading.
Yeah. That relates to like the thing we did with the world models, where somebody found that a random network captured a large part of the sort of the semantics of the world models paper too. I was curious, have you ever tried running it in reverse, like it's flipping the style image and the content image? So, for example, you could take something, say, like an animation, and then take a natural image and see if it sort of like fills in the sort of, so you get like a 2D graphic and you give it a natural image and see if it kind of like makes the flat image look more real.
Yeah, I've kind of tried it, and it doesn't look as cool as going the other direction, but it kind of works. It just looks a little bit funny. In particular, I think what works well is a very repeated characteristic that can kind of be summarized in these summary statistics. So
even just color, right?
Yeah, solid. Yeah.
Yeah, but I thought if you had like ocean, grass, sky, maybe it would sort of like get the textures out of those and transfer them onto the drawings.
Clouds.
Yeah, just a thought.
So, a while ago they were showing in this meetup different kind of network that can do something very similar. So I want you to, a little bit, if you can talk about the differences. So it was shown that you can do similar things with GAN's network. Generative adversarial networks. They were also showing two images and then showing how one can become like trained and one can become like take the style of one, let's say daylight and night, and transform another image to more that is taken at night to look in daylight or vice versa, things like this. So this is also like taking the style of one image and applying it to the other. Here you also do something somewhat similar, but not exactly. Can you talk about a little bit differences?
Yeah. So one of the main differences is that this is totally like all transfer learning. We're only using the weights and parameters from the VGG network and utilizing them. So like how that network would perceive an image in order to do the transformation. Those, at least to my knowledge, I'm not exactly specifically sure what you're talking about, but what I believe that is it might have been this paper by Adobe Research, and it was cool, but they're taking a whole bunch of examples of, say, images of landscapes at night and images of landscapes during the day, and then calibrating a function to transform from one to the other. And that would be the main difference of the approach, that like you're designing a network to do that specific thing, whereas here you're just taking a network that's already been designed and running some different type of calculations on it in order to do the transformation.
But you also have the same several ideas that are the same. They also start with random numbers just to start generating the image, and you also have random numbers here, but your random numbers here are a little bit different, correct? Or
yeah, so like in the paper written by Leon Gattias in 2015, they're utilizing the random noise to start with. And the kind of methodology I'm proposing, you don't begin with random noise.
So there's no random, like, what's the randomness here used?
In this, there's no randomness. But what I believe for the GAN methodology, they're using randomness in a latent vector. So they're taking some input and projecting it, figuring out ways to project it into a latent space, and then you can draw
They learn the image from this randomness. The random numbers are just a random vector to generate an image that looks like the original and then whatever. But here, so here you're basically using random numbers just for optimization, or you start
not using any random numbers.
Two pictures.
Hmm?
Two pictures and you make one look like the other. It's
Yeah, I'm trying to figure. Yeah,
No random
they're also
number.
doing it there, but they're doing it in different ways.
Well, they're just doing a different thing. I mean, they're just trying to basically generate adversarial examples, just then learn to discriminate. Here you're just trying to morph two images into each other.
So here you just intervene in the optimization process. This is what you're doing.
Say that once more.
You just intervene in the optimization process of the network.
Pretty much, yeah. You're taking what has been learned, a network that's been learned to classify certain images, and you're kind of looking into the middle of its process. So like you're having it run the steps it would take in order to classify something, and you're extracting the activations of those intermediate neurons, and you're calculating some statistics based on those. Based on those statistics, you're calculating distances from one image to another image and modifying them such that there's convergence in those aggregate statistics. So it's a different approach.
Have you tried it with different architectures to see how that impacts?
I haven't.
Yeah.
I think it would work all right, but the nice thing about VGG is it's like it's very clear what your state is at any given point. So. And the states are quite large in terms of data and number of features, and so that's why I've stuck with that. If I had more time or really a reason, I would try some other architectures. I just haven't gotten around to it.
Cool.
Is there a way to try shallower or a different number of layers? Like the depth, because it seems like the depth would have some influence in the kind of style transfer. Is that
totally? Yeah. So I have so for example, in the GitHub, I wanted this one to run pretty quick, and so this one is done with just the very shallow layers, so only the shapes, only kind of more basic geometric characteristics rather than more abstract ones.
So how much depth did you do for that one?
Let's see. So this one took 50 seconds, and it was less than 50 steps. Is all I can remember. I'm not sure if it converged prior to 50 steps, but I set it up to run to up to 50 steps, unless it converged prior.
Okay, so it's fewer steps, but as far as the depth, was it still the same?
This, I just can't remember offhand, but I want to say this was the first 4 layers or something.
Okay. You could sell that.
It's all yours. The plain style transfer uses regular L2 distance. Honestly, I haven't noticed the difference. What was your motivation to compute the statistics and to optimize the weather studies rather than plain?
It kind of just didn't really make sense to me. Their approach was using these non-central second moments, and I was trying to reproduce it, and I was frustrated that, in their paper they said, okay, this ratio of A and B.
And they don't say how they came up with those numbers? Or?
Exactly, yeah, they don't at all. So it's these specific ratios of alpha to beta work in order to generate these images. So if you wanted to try it on a different image, you would need to play around with, it's a pretty big space from 1 times 10 to the negative third to 5 times 10 to the negative fourth. You'd have to try a whole bunch of different parameters. And, I thought maybe cleaning up the math would solve that problem.
Did you try those images?
Not exactly. I think I have tried some of them. I just, I have this one here. So with the Van Gogh.
Cool.
Well, so it works pretty well there. And so then these are all done with exactly the same settings and no parameters tuned whatsoever. So I think it generalizes pretty well.
If you wanted to do this for music, as you said before, I'd say the biggest missing piece is the analog of the VGG net for music.
Exactly.
Do you know of any such network that's trained on music? Or could you even say, what was VGG net trained on? It was classification for...
Yeah.
Just
So it'd be like somebody who spends a lot of time and builds a really big, large data set of like, you know, hundreds of thousands, if not millions of songs with certain attributes that you could predict, and then trains a very big, there's like, I've actually messed around with it a little bit. I think it's tough to say what the architecture is, but yeah, I'll leave it at that. I kind of tried and I didn't get very far. The main thing is, I think, really building up the data set of music and, you know, having it all be well categorized and so forth, but then also finding the right architecture of like how exactly you want to do your convolution in 2 dimensions and 1 dimension, you know, and
There was a paper a couple of like, within the last 2 months, possibly only a few weeks ago. It was the one where they do a sort of like a stacked wave net, and that they were using that for like analyzing like long range structure of music. Although then again, what I think Abe found when that most of the people trying to replicate WaveNet are not really having a whole lot of luck. So your mileage may vary.
Yeah, so like we might not have like the open source data set, but like if you're Spotify or like Apple Music or something,
Yeah.
they already have all these like music with probably a whole bunch of extra data categorizing them. So
yeah, and it could even be unsupervised, like just
yeah,
knowing who listened to what, and you know.
Well, not necessarily even that. You could do kind of like auto prediction. You run music through
take
it,
this song,
and
make it more
predict
popular.
No, make a version more specifically of the song with like.
All right, any other questions?
Yeah. You said in the beginning you were interested in edge machine learning. Can you talk about what particularly interests you with that?
Yeah, I think it's really interesting. I've been following a little bit of like ARM Holdings is talking about this new set of Trillium chips. Basically, I think the main observation is that the cost of communication in terms of you know, both like the chip cost to communicate and subscribe to certain infrastructure, and then also the power cost. It seems like we've reached a point where that's probably not going down, whereas the cost of compute locally, in terms of chip cost and then also in terms of power cost, is going down dramatically. So I've been thinking more and more, like, it's one of those things where I feel like it's gonna happen, but the specifics of it are to be determined. I think we're going to have a lot of smart chips, you know, distributed, either, you know, probably integrated into phones in some extent, but then also into various other sensors, some of which seem like really creepy and scary and dystopian, but then some of which maybe are able to enable a lot of cool things. So I've been thinking a little bit about compression. So the notion of like, let's say you have a camera that most of the time is staring at the same thing. How to develop networks that could compress that when entropy is low, or like it has a very high probability input, but then also be able to reproduce with high fidelity, low probability events. So it's kind of taking an information theory approach to compression. So the idea is, like, if you have a security camera, you don't care about 99% of the footage because it's staring at a wall, but you care when, you know, something walks by. So like, how to design the network to be sparse and just have a very simple message that it needs to send up to a network, or send no message at all when things are very regular, but then not necessarily switch into a mode, but move somewhere on a scale when you have a very low probability of that, to be able to, you know, represent that image with high fidelity. So
But the MPEG does this already.
What's up?
The compression already does this for you.
MPEG compression, I think you can improve it, but I can't prove it yet.
No, not proof. It's like what it does is actually every once in a while, if you have something change in the image, it will generate a new image from. It will insert the entire image from scratch, a JPEG, and then otherwise it will only give you the deltas.
In MPEG.
Any
Yeah.
modern compression technique will do this for you already.
Yeah.
It only gives you the differences.
I'm thinking about a little bit of a different approach, but
Okay.
yeah.
I think he wants to detect bad guys walking by and, you know, normal good guys.
Yeah, just look at the epic and see where it inserts in the JPEG. It's like, this is the new one.
Thanks, Vincent. That was really cool talk. I really enjoyed that. Just, I forgot to mention before, typically we go down to CU29, which is right across the street, for a drink. It's a cocktail bar, pretty good stuff. We usually have a pretty good discussion, so we'll go from here to there. Grab some pizza. There's plenty left over, and feel free to take any home or drinks or whatever. Thank you so much for coming out.
Python repository hasn't changed in years. Is that because it's done, or is that because it's abandoned?
Probably abandoned, because Neo has kind of been abandoned.
Because beauty grad housing is over there.
So, did I mention it when we were in there?
Yeah, well, the talk was about Neo, so, but as far as I know, Neo is pretty much abandoned at this point.
Probably at the paper meetup or something.
Yeah, I'll be at the
because like, because you can do CNN on GPUs, you can't do Meet on GPUs. So it's so much more expensive and more time consuming to train using, well, at least pure evolution. I mean, I guess there's some modification.
So it's a hardware issue.
Well,
you can't do
issue
efficiently right now.
Yeah, if you can't do it, well, even if it's better, if you can't do it as well as you could on a GPU or any other method, then yeah. Maybe you want to write a paper where you're like, oh, the average stuff,
that was really cool. So I either can come to oh, very, very cool. I think you can have this once you start it, it's going to be like something you can do yourself. But you can have one of you guys.
Okay,
probably for a little bit.
Oh, well, maybe that was indirect. I'll make a direct introduction.
Okay.
Figure it out.
It may be even the same person.
Is he the same? Because they're.
I don't know.
I mean,
yeah, basically.
I was wondering what your but he's in language. I did some this was I love non-pair. Yeah, those are I hate prayer. They're just they're very inelegant. Like there's something so inelegant about. I mean, in a sense, it's not a completely specified algorithm. Right? It's like add a hyperparameter search to make it a complete algorithm. Yeah, that was really neat. And it seems
so that
yeah,
language without you could just do it using
well, in theory, you probably could, but it wouldn't necessarily work at the global level. Yeah, I don't know. I mean, if it does work, it would be much faster. Yeah, there was an interesting
although I guess because the problem with the wavelength will be that it's not. Well, no, there are over-complete spaces where the wavelength is not as over-parameterized. I mean, the point of the CN, I think the point of the thing where he's doing the box is that it's highly over-parameterized. Right? So he has like for every pixel in the image, he basically has like all the and that's why he can do that's where the one is. Whereas if you have at least if you have a standard wavelength, then you'd have as many pixels in the training as you do. So you wouldn't get the. So you have to do something different. But there are families of wavelengths.
So since he's using, actually, while we're listening, since it's a two-dimensional Gaussian, does it mean that pixels in the middle have more integrity? Or is it really just that he's trying to find the
It's not the Gaussian of the Gaussian over like the correlations of the
Basically, similarity
So he has like, it's like the original image, and then he has like, all the like, what does each convolution layer get at that position? So sort of like close that, close each pixel, and then for each convolution layer you get like a whole bunch of activation. So one pixel gives you like a whole ton of activation. And then for all of the pixels, he kind of treats those weights as a distribution. Actually, I'm not sure. Is he treating the matrix this way? Is he treating this way? Well, he's got like the activations in the stack of the convolution of that. So it's basically like you have a convolution thing which is sliding around. And so the point is he's looking at like the activations of the convolution layer as applied at that pixel, right? Okay.
Right, he's taking the second moment across each layer.
Right, but then he stacks it, but then he does the correlation. And what I'm not sure is he's doing the correlation where the positions of the samples and the activations for the features or the other way.
I think he's just taking the moments at each layer and looking at the difference, right?
So I think he actually gave an example. You get 28 by 28 by 512.
So 28 by 28 was the convolution layer. 512 was the image.
28 by 28 was the giant image size.
Oh no, that's the original. Oh, so it's a tiny image.
That's got to be the image size at that layer for this image.
Well, that's the convolution
right?
So that's the
Right.
convolution.
You're 512-bit samples at each bit.
But even 512 is not like it's not a 500.
No, the image at that layer, the image is 20, and the depth, the image, the number of bits per pixel at that layer is right. You're going from just a few bits per pixel and a lot of pixels to a few pixels and a lot of bits.
Like a whole convolution layer. He's picking a layer in the convolution.
Each one, yeah. He's doing all of them, and then adding the total distance across all the layers.
The way I understood it is that each layer has its own
yeah.
I could see I'm Freya.
And one captured the semantics, and so it was actually the difference in the block function. So it was sort of like your image space is decomposed into like the style subspace and the semantic subspace, like an even given find one that's all the way down. One way is
no, I've been curious. Yeah. Well,
great. The first moment. That's essentially what it
But I definitely don't have the answer to the right architecture. So how's the sort of
more adventures. So, gone from nearly background, hopefully fine.
I talked to you about it. Now if you asked me some days ago, I would have said,
yeah, that's it. The last time I talked to everyone was
Coworker, not
so, like, we worked together like 15 years ago, we've known each other forever. We kind of got hired together. But it's kind of hired together, but why we kind of started actually that. And we were at that other company, and then we kind of got hired together and started also together at this company.
And their concept was what you want.
And also they,
it's
like that.
So you said that the deal was restructured, or the project looking again?
They kind of pivoted the company. They were like now they have an actual client.
It was actually
plans
given like my level knowledge.
We found an optimal transport line of information from my knowledge to what I needed.
Alright, have a good night, guys.
But the fact that they, yeah, it was kind of rather than just getting friends.
What's your day job? Is
So how big was the team again?
Maybe I see it, they can like freeze me or something.
How did you get into this?
Yeah, right.
I got interested in it close to 2 years ago. I just started reading various things, took a couple of online courses.
Sorry to hear that.
Parametric algorithms are so elegant.
That's how I feel.
I really like this.
I was asking about the topic because there's a recent paper on optical transport, actually 2 of them. One is by Courtney and the other one is on structural. But they work on subnets where multiple points from one sequence to correspond to density at every single point.
Whereas it was kind of like, yeah, no, this is going great, this is going great.
Yeah, I have to read it to know exactly what they mean, but coupling is just a general way, you know, at least as I understand it, say, you know, a subset of that, joint distribution, which is distribution, that's called the coupling. Yeah, and you could have, like, the multiplicity.
I'm not really sure what the power is
or like a number of samples that your software, you get what I'm saying? So that's what I need to figure out.
I don't know all those guys.
If you have optimal transport problems,
Things laid off dimensionalities. I don't know if there's actually paperwork that goes along. I fire anybody at any given point.
I was curious whether it would also work in
Sorry to hear that.
where it would
Hopefully
be
businesses
maybe if
are
their
is your
loyalty
is your loyalty,
yeah, something like that.
your demeanor and what you're saying
You need to find some sort of way of figuring out what
It's not at its peak.
It also works really well when you're trying to transport distribution. It looks kind of similar.
I mean,
Like you
what
have to concentrate
sucks even more for so the other
but
guy,
it fails really badly when the distributions are like totally
his wife's approaching 14.
like one is highly skewed, the other is not.
Yeah, it's like some, you know, like there have to be some topological
It seems so generally,
I love the surface.
Yeah, there's no objective measure, but
The son of wave chip paper?
I think everyone here would agree that Conan Solomon and all of that.
That was
It's terrible.
Probably one reason not to have
wave, like that, like wouldn't hire a couple usually they focus on the breakout. Yeah, it's like it's unclear that like there was yeah, it didn't you know whatever the picture like it looked like the picture of sorry, some of those might have just been outside the
I was, so like now.
It's like more art.
I think it's summit. So this
we're using regular neural nets, it's because of the deep mind. They've influenced the entire field.
I don't know what to say. This is
they
one of the
could have
crazy
chosen
stories I've heard about.
completely something
Right.
like this. They could have chosen something like that.
Yeah, but it is, yeah, the annoying thing about it is that all of the reasons they kind of gave
Deep learning mixed with
were apparent.
that kind of fixed the topology.
So they have like
The culture doesn't work
either realigning do something or at least give warning as in like it was really like
I know of a company here in town, they no longer exist, but there was a CEO who always wanted to tell because so internally within the board and a few other people knew that time things were about to start being cut, but
which is really cheap.
the CEO
really
not
wants to
really like it, and how this is culminating is that what could have happened originally could have laid off a person or two. Never one thing about this is what he did is that burn rate never
whatever different activities that is infinite.
Yeah.
All the workers one day.
And that's always been very.
This was here in town, and they would show up one day and silent
For a long time stay on fixed topology is because of my
because the guy didn't want to give back here. And that one is close to breakable because they knew it could happen.
It was just a random.
Yeah, it was a incredible stuff.
Yeah.
Sometimes you ask people, hey, were you willing to take a pay cut? Some people will want to.
Yeah, that must be.
I actually talked to them.
Yeah.
The other guys
because Google started making filters. Even TPUs are still they're mainly geared towards maintenance.
Yes.
So
and so
only fixed topology works for
right. And
so I think
for dynamic policies, ultimately would be the right solution, or ultimately will allow you to be much more efficient. And they're going to be costing all the only solve
yeah, I mean the NVIDIA. Not gonna lie, they'll
the three of us
or they'll force culture.
Well, what will happen is
I said all the vegetarians.
Which is good. I already reaching even like all the reinforcement problems.
I mean, most of them, reinforcement learning, I also do a lot of work with natural language. And natural language, obviously, you have very distant correlations.
You're right. There
where the traditional, just a simple unrolling doesn't work.
This is that Indeed.
Not just Indeed, but it's
Okay.
like, because, my company and we're doing like contract mediation.
Oh, okay.